Okay, let's think about the spectrum, and especially for fluorescence case. Okay, so here is one of the example of the absorption and the fluorescence spectrum of, in this case, anthracene, right? And then the green curve shows the absorption, and red curve shows the fluorescence spectrum, okay? And it's around 300 to 400 nanometer. And you could see the shape of absorption and the fluorescence spectra are kind of symmetrical, centered around here. You could see some of the oscillation pattern in the spectrum. And what are they? Okay. So in the absorption, let me remind you that the Frank-Condon principle and also the reaction coordinate. And as you see that in the absorption process, always absorption starts from the ground state, vibrationally ground state of ground state, right? S0. And then it could go to the V dash equals 0. It's a vibrational state of the excited state. This is one state, okay? So this is S0, this is S1. So it could go to from V equals 0 to V dash equals 0. But also, depending on the molecular structure, it could go to the V dash equal 1 or V dash equal 2, right? This one, these correspond to the absorption spectrum oscillation, okay? So that, and it can write as this one is 0, 0 transition, meaning the V equals 0 to V dash equals 0. So 0, 1 transition, 0, 2 transition, and 0, 3 transition, like this. So this oscillation shape comes from the vibrational state of the excited state. So that's the absorption spectrum. On the other hand, thinking about the fluorescence spectrum, so fluorescence spectrum always mostly comes from the vibrational ground state of the S1 state. However, it can go to the, of course, V equals 0, V equals 1, V equals 2, right? That's why in the same as the absorption spectrum, in the fluorescence spectrum also has some oscillation. And I would like to remind you that the V equals 0 to V equals 0, V dash equals 0 case is same for absorption and the fluorescence. That's why you have the common peak in the absorption and the fluorescence, and the other oscillation peaks correspond to the vibrational state for the ground state in the case of fluorescence. Okay. So when you have an absorption and fluorescence spectrum, and if they have some symmetry shape, it's you could understand and the vibrational energy level of the molecule. So the next things we're going to study is the inter-system crossing. which is kind of really important in photochemical processes, actually, because many of the photochemical reactions actually start from the triplet state. And also triplet state is sometimes important to the light emitting device. So let's study this. However, if you remember correctly, that from S1 to T1 state, which involves the spin number change, right? From S equal 1 to S equal 3. So this is a forbidden transition based on the quantum theory. However, and this is still true, but this transition is partly allowed due to the spin orbital interaction. So here's the things. So there are two main reasons why this intersystem crossing happens. And first one is S1T2 transition. So this is a case, one of the most famous molecules in the photochemistry is benzophenone. Right? And if you draw this one could happen because, for example, E0, S1, and then S2, and T1. How can I draw? Somehow T1, T2. So triplet state is always lower than the same number of the singlet state, but somehow by chance the S1 and the T2 level are quite similar in energy. That could happen. So this is in this case, there's a chance to for S1 is changed into the T2 and in coming to T1 state. That's why it could have a very high probability of the triplet formation. Okay. So why does this happen? So let's think about this. First, S1's, since this one is a carbonyl molecules, I would like you to remind you that the molecular orbital we have to think about is pi and n and pi star, right? And in the ground state, the electron is occupied like this. However, the S1 state, one of the electrons are going up like this. So this is S1 state, right? And I would like to emphasize that these two, the electron spin is opposite. That's why it's singlet state. On the other hand, the second excited state, let's think about. Second excited state would be you could excite the pi electrons to the pi star state. And we want to think about the triplet state. That's why think about these two electrons has a parallel configuration because this is triplet state. Okay. So what happened in a S1 and a T2 transition is the first think about this. So since these two electron configuration has quite similar energy, the energy electron can be easily changed, like this one and this one can be kind of exchangeable. And then that means this electron is coming this way or coming this way. So it's since S1 and T2 are switching the state frequently. And in this case, you could think like this pi electron and n electrons are exchanging. And pi electron is extending in a CO bond, but n electron is localized to at the oxygen side, as we studied. Meaning that this exchange induce the electron distribution change, electron distribution change in a molecule, right? So if the electron shape large change for kind of very large, it could induce the magnetic field because always the electric field and the magnetic field is kind of inter-exchangeable. So the electron configuration change, the magnetic field is induced. That's why these two electrons the spin change. Now this one first, spin change. Like this. So then I could summarize like this. So due to the large electron distribution change could induce the spin flip due to the induced magnetic field. That's the one of the reason. And actually for benzophenone has almost 100% the triplet efficiency. Okay. The other reason for triplet formation is called the heavy atom effect. Heavy atom effect. This one more simple. Let's think about if you have nuclei, and in high school we study electrons moving around the nuclei, right? And if you look at this centered from electron, okay. So if you have put a electron in center, it's like the positive charge. Nuclei is rotating around the electron, right? And if the positive charge rotating, it gives the magnetic field in like this. This magnetic field could, again, similar as the previous the S1T2 transition, it could the spin change of electron. This could happen in any of the atoms you could think, but actually that this is very efficient when this is a heavy atom, meaning the large amount of positive charge That's why this effect is stronger for the heavier atoms. That's why it is called the heavy atom effect. So in summary, anyway, due to the electron, this is called a spin orbital interaction. So large orbital change, meaning the electron cloud change, could induce a magnetic field. That's why that sometimes electron spin can be flipped. That could change. That is the mechanism for the spin change, meaning the singlet, triplet,